Wednesday, we stop at the preparation of alkene, right? And I saw people already submit the homework and they look quite okay to me. And today we'll start with the reaction of alkenes. See, we have about 57 people in here, which is about the same number as people submit the homework, the first homework that I checked this morning. Okay. But actually, I think the class have like almost 90 people register, right? This class. 60 people in now. Okay, let's start with the reaction of alkene. The most important reaction for alkene is the addition reaction, which involves the reaction of double bond with the reagents that the pi bond of the double bond will be broken and the groups in this case is X and Y will be added and form sigma bond with the carbon atoms of the original double bond here, as you can see, and we call these addition. You can see that in addition reaction, okay, people want me to record. I tend to forget this. Thank you. Let me record it. How can I get back to the Zoom window and record it?
Recording in progress.
Okay, we record it. Oh, by the way, has the video come up in Expo 360? Has it come up for the last lecture? Okay, so it's working. Now we'll miss some up at the beginning, so don't mind me if please remind me each time when I start the lecture. Sometimes I forget about this turning on the recording. Okay, thank you very much for reminding. Okay, so I'll say it again. In the reaction of alkene, we have the addition of the reagent. In this case, is XY, which will add into the pi bond to
You're
form.
not sharing the screen.
What?
You're not sharing the screen.
The screen not coming out.
It's the Zoom screen. It's not the presentation screen.
Oh, sorry. Let's see. Okay, is it coming out?
Yes.
Okay, sorry. I'm still not very good on this function, right? Okay. Okay. So after the addition, you see the double bond turn into a single bond. And there's two new groups, in this case, X and Y added to the alkene. And you can see that in addition reaction, you don't get any other byproduct, unlike the substitution reaction that you have learned in the alkyl halide, that in the substitution reaction, you get some other byproduct formed from the leaving group, right? But in this case, everything combined to form one compound here. Since the pi bond is quite electron rich, so the reagent here, XY, usually is electrophile. It like to react with the electrons of the pi bond. So the alkene itself act as a nucleophile. Okay. But in some case, you can perform radical reaction as well, as you will see later on. Okay, in the addition of alkene, you have two modes of addition. One, we call it as a syn addition, which X and Y adding on alkene from the same side, which we call syn addition. But if X and Y group add at the opposite direction, you get the anti-addition here. This will affect the stereochemistry outcome of the products, as you will see, and you have to kind of understand and memorize some of it, which reaction perform the syn addition and which reaction perform anti-addition. Okay. Here, the first reaction is hydrogenation. Hydrogenation usually requires some catalyst, so we call it as the catalytic hydrogenation. The hydrogen molecule itself cannot add directly onto alkene. You need some metal catalyst to activate both alkene and hydrogen molecule to break this pi bond and the sigma bond between the hydrogen, and add the hydrogen atom to this alkene structure. Normally, in the catalytic hydrogenation, the metal used are palladium, platinum, and nickel. Okay, and the addition is a syn addition, which means both hydrogen will add from the same side of the alkene. For the terminal alkene, you won't see any difference of the product from the syn or anti-addition, because the terminal alkene have two hydrogen atoms here. So you cannot really tell whether it's syn or anti. But on this molecule, the cyclic alkene with two methyl substituent, you can see that the product from syn addition will give you the cis compound of dimethyl cyclohexane here. Okay. Okay. People cannot see which slide you want me to turn back to, that you cannot write down or draw the structure. Did I go too fast? Someone put in the chat that want me to turn back the slide. Which slide number? Can you say? Can you get these structure, these two structures? Okay, it's okay now. So now you can tell this reaction is syn addition because the hydrogen is on the same side. That make the methyl group, the original substituent, become the cis isomers, okay, on cyclohexane. Okay, the mechanism for hydrogenation is shown in this video. Okay, I'll go slower. People say I go too fast. Okay, from this video, you see that the metal sheet here bind with alkene and break the pi bond, okay, to form the sigma bond with the surface of the metal first, and then the hydrogen atoms also form the sigma bond with the metal surface. The sigma bond between the hydrogen molecule also broken here, as you can see. And then the hydrogen atom slide on the surface to add onto the alkene from the same side. So you get the syn addition. Okay, do you get the picture? Yeah, according to the mechanism, it's explained the mode of addition being syn addition, and also is also explained the reactivity of the alkene, that when you have more substituents, it will go slower for the catalytic hydrogenation because the substituent will kind of inhibit the binding between the alkene with the metal surface, because when it's bulky, it will be harder for alkene to bind onto the surface of the metal. So the terminal alkene here, the one on the left, will be the most reactive, and the theta substituted alkene will be the one with the least reactive. And in fact, the theta substituent will be very hard. You need maybe quite high temperature as well as the pressure of hydrogen to perform the hydrogenation. This hydrogenation is quite useful in industry. It used for the hydrogenation of the vegetable oil. The natural vegetable oil usually contain some unsaturation, as you call it, as a unsaturated fat. You heard of it because it has some double bond in the fatty acid side chain here. And this double bond can be added with hydrogen under catalytic hydrogenation condition, and you get the conversion from alkene to alkane here. And this process usually get some competitive reaction as well, as you can see from the mechanism here. Although I said the reaction is go by syn addition, you can see here one hydrogen, but it goes stepwise. One hydrogen atom at first, the second hydrogen atom at later. Sometimes this process allow the bond to rotate and the hydrogen add from the other side because it's reversible, you know. So sometimes you get competitive reaction of the the rotation and elimination of hydrogen, and you get some trans alkene as a competitive product. And we get the trans fat, which is a very bad fat or lipid for your health because it stimulates cholesterol synthesis and can cause some heart disease, as you probably already know, especially for the kind of margarine products. It contains saturated fat as well as some trans fat. Okay, that's one example of the addition reaction, which is also useful for food industry. There are also several more of addition reaction that we will learn. The first one is the addition of the hydrogen halide, which we call is a halogenation. So you get hydrogen and halide atoms on the cyclohexane ring here, because we start from cyclohexene. And the addition of water molecule, you get the reaction which is called hydration. And the group that add on to the double bond is a hydrogen and OH group. So you get alcohol as a product here. The addition of halogen, which is called halogenation, you get both halogen atoms on the double bond. It's convert double bond into a single bond here, okay? But if you perform the reaction in water, the halogenation normally performed in organic solvent, okay? But if you change the solvent into a water, you get another kind of product, which is called halohydrin, which is the addition of one halogen atom and another groups of hydroxyl group coming from water, okay? Another useful reaction, which is called hydroboration, which is the addition of borane, hydrogen, and boron. That's the first step. And then followed by the oxidation in the second step using hydrogen peroxide, you get also alcohol. Okay, so actually this last reaction gives the same product as the second reaction here as a hydration. But in details, when we study about this reaction one by one, I'll talk later, you will see that the stereochemistry and regioselectivity will be different, okay? Let's start with the simplest one, the addition of hydrogen and halide here. So when you add the hydrogen halide, you get one atom of hydrogen on carbon and halide, in this case it's bromine, on another carbon. This is simple, right? If you use a hydrogen chloride, you get alkyl chloride product. So far still easy, right? Okay. And we call this as a electrophilic addition because it starts with the addition of the electrophile. For this reagent, hydrogen and bromine, which part of the molecule will act as an electrophile? Can you tell? Hydrogen or bromine?
Hydrogen.
Hydrogen, right? Electrophile, that means love electron or it's love negative charge. So it should be a positively polar, right? Which is hydrogen will be partially positive and bromide will be partially negative according to the electron negativity, right? So the hydrogen part will act as an electrophile in this case. So you add on to the pi bond first, which is electron rich part of the alkene, and you get the intermediate here as a carbocation. Okay, and you should note that when we draw the mechanism, we normally draw the arrow from the electron to the atom that the electron attack, instead of the arrow pointing from hydrogen to alkene. That will be wrong writing, okay? You should draw from the direction of the electron to attack atom, not atom attack electron. You understand? Okay, so the curved arrow should go from the double bond to the hydrogen atoms here, and the electrons of the sigma bond go onto the bromide to form the bromide anion here. Okay, and then the bromide anion attack the carbocation to form the products here, the alkyl bromide. Okay, in the second step, so the carbocation is act as an intermediate in this reaction. And the bromide act as the nucleophile in the second step. But we call the mechanism of the reaction according to the first step. So we call it as an electrophilic addition. Okay. Can you write them all? Can I move to the next slide? Okay, one important thing about this reaction is similar to the reaction you learned before, that whenever you have a carbocation intermediate, you have to be careful about the rearrangement reaction. Do you know rearrangement reaction? Have you learned about rearrangement? Hello? Are you all with me?
Rearrangement reactions?
Yeah, have you learned about the rearrangement of the carbocation in the reaction of alkyl halide? When you have a SN1 reaction?
Do you mean to say like the nucleophile can attack from the top and the bottom? That thing?
No, when you form the carbocation, which is not stable enough, it can have some atoms in the structure of carbocation to move to the position of the carbocation and form a new and more stable carbocation. Have Ajahn would talk about this before?
No. Learned it.
No?
Oh, no.
Okay. This is one important caution in the organic synthesis. When you apply some reaction, if you get the carbocation intermediate, and have you learned about the stability of carbocation?
Yes.
Okay, so which one is the most stable?
The tertiary one.
One with the more groups on it.
Yeah, more substituent or the tertiary one, right? Okay, the tertiary one is the most stable, and then the secondary and then the primary is the least stable. Actually, the primary is very unstable and they don't even know whether it really exists, because whenever if it try to form primary carbocation, it just does not form at all, undergo SN2, as you have probably already learned, right? But from secondary and tertiary, you can form carbocation. In this case, what kind of carbocation here? Can you tell?
Secondary.
Yes, it's secondary carbocation. You have two alkyl group attached to the carbon, right, of the carbocation. So we call it secondary carbocation, which is somewhat stable, but there's something else more stable, which is a tertiary carbocation. If you can move atoms like hydrogen atom here to the carbocation and get a more get tertiary carbocation, that can happen. But in this case, if you move hydrogen, you get the same secondary carbocation. So there's no point for the rearrangement. We'll talk more about rearrangement later, because I thought you learned some of this. Now it's just introduction of that rearrangement. So when the rearrangement occurs, you will get the product which you probably not expected for. Okay. Now for these simple compound, the symmetrical alkene, you get only one product here. Okay, and you don't have rearrangement. Okay, let's move on to another example, which is a little bit more complex here, because you have unsymmetrical alkene on carbon 1 and 2 of the double bond. One side you have one substituent, the other side you don't have substituent here. So when you add hydrogen, you can either add onto the carbon number 1 or carbon number 2, and each one will lead to different products, right? As you can see, if the hydrogen add to carbon number 2, you get the first product here, which is 1 chloropropane. But if the hydrogen add to carbon number 1, the chloride will go to carbon number 2, and you get 2 chloropropane. Theoretically, which one you think you get more?
2.
Yeah, if you learn about stability of the carbocation, you will be able to predict that you get the 2 more than the 1. Okay, and what they observe is that the 2 chloropropane is the only product or major product in this reaction. The person who observed this is Markovnikov, and he has a rule at that time. There's no mechanism known for this type of reaction, and people did not know about the carbocation and things. So his simple rule is just that when you add the hydrogen halide onto unsymmetrical alkene, the hydrogen atom will go on to the carbon that already have greater number of hydrogen there. In this case, it will go into onto the carbon number 1, yeah, which have 2 hydrogen to begin with, right? On carbon number 1, it has only 1 hydrogen there. So this is his rule. But after people learn about the mechanism of this reaction that is undergo through the carbocation, we can explain his rule by using the stability of the carbocation. Let's look at the first option here. If the hydrogen add to the internal carbon here, you get the primary carbocation, which we say is very unstable, right? But if the hydrogen add to the terminal carbon here, you get secondary carbocation, which is more stable. That's why it forms this secondary carbocation, and the chloride can attack at the secondary carbocation to form the product that we observe, which is a 2-chloropropane here. Okay. Can you follow?
Yes.
Okay. So now the Markovnikov rule has been rationalized based on the carbocation stability. So from now on, when we talk about Markovnikov product or Markovnikov rule, we'll look at the stability of the carbocation instead of the number of hydrogen on the carbon. Okay. The rule has been modified based on the stability of the carbon rather than just simple looking at the number of hydrogen on carbon. Okay. Because that is a simple suggestion. Sometimes it does not hold in some alkene, but for looking at the stability of carbocation, it can explain broader products of the reaction. Okay. Now let's look at the hydrochlorination of this compound that you will get. Okay, you can get the addition from the first. You have to look hydrogen. Which carbon will it add to? This carbon or the carbon with the methyl substituent here? Which side? The left or the right?
Left. Left.
Left, right? Because it will give you a tertiary carbocation here, right? Which is more stable than if you add the hydrogen to this carbon, you get secondary carbocation. Okay, so this follow the Markovnikov rule. So you get this, but now we'll look at the site that it will attack, whether it's from above or from the bottom. You get either this compound, the red hydrogen on the top, or the red hydrogen is at the bottom, which means the hydrogen is coming from above or below the plane of the alkene. Okay, but this first step will not affect the stereochemistry, right? Because you have 2 hydrogen here, and this carbon is not chiral. Okay, but in the second step, the chloride can also attack from above or below the plane, and you get 2 products, either chlorine on top or chlorine at the bottom here. Okay, but you already learned that carbocation, what type of geometry does it have?
Trigonal planar.
Trigonal planar. That means it's plane, right? So you have the same probability or same chance for the reagent to coming from the above and below the plane. So you get the same amount of product here, which means you get what kind of product. This carbon become chiral now, as you can see. You learned about stereochemistry before?
Yes.
Okay, this carbon is chiral, right? This one is R or S. Can you tell? Let's check whether you still remember about the configuration assignment. This is R or S.
S.
The first priority is choline, right? This is number 1, number 2, number 3, and number 4, right? Number 4 is behind, so it's S. Choline go to number 2. This is S, and this is R. You get 2 compounds with the same amount. What do we call it? When you get 2 enantiomer at 50 to 50, what do we call?
Racemic.
Yes, you get the racemic mixture of the enantiomer here, A and B. Okay, so for this reaction, you get racemic mixture because it goes through the carbocation. And also there's a simple rule that they call rule of thumb, that whenever if your starting material is a chiral or not a chiral, okay, and your reagent also non-chiral, you will always either get a chiral compound or racemic mixture. That means it has no optical activity. Okay. Okay. The addition of hydrogen bromide can also be performed under free radical condition by using peroxide along with the hydrogen bromide. Okay. And only hydrogen bromide that work for this type of reaction. The hydrogen chloride, it will not undergo radical reaction. It will undergo according to the previous mechanism, the electrophilic addition, because the HCl bond is too strong, stronger than HBr bond, and you will get the product according to Markovnikov rule. But if it goes through the free radical reaction, you get another type of product, which we call anti-Markovnikov, which we will see later what is an anti-Markovnikov and how does it form. Okay, how about HI? The HI bond is also too weak, so it tends to break off to form, it too acidic, it tends to form H plus or the proton easily, and it adds quickly to the alkene. It does not wait for the peroxide to react with it. Okay, so you get also for HI, you get electrophilic addition. That means the peroxide reaction only work for HBr, and you will see here how does it work. Okay, it starting from peroxide. Peroxide is a compound with the oxygen bond here. This oxygen bond is quite weak. You can heat it around like 100 degrees Celsius and it will break to form the radical. You have learned this before, right? In the radical substitution of the alkane. Have you learned about it?
No, we didn't do radical substitution.
Yeah, but you see the radical of the bromine radical before, right? When you activate it with light. Have you seen that? Chlorine and bromine, when you shine the light, the bond between chlorine and bromine break and form free radical.
Yeah, we did that last year.
Yeah, okay. That is similar to oxygen-oxygen bond. This single bond is quite weak. You can either heat it or you use the light to shine on it, and you get the free radical here. The oxy radical will abstract the hydrogen from HBr to form the bromine radical. Okay, the bromine radical will add onto this alkene. This is unsymmetrical alkene. Which side you think it will add to? This left side or right side of carbon? The left or the right one? If you add to the left one, you get secondary radical here. But if you add to the right one, you get the tertiary radical here. Radical stability is similar to carbocation stability. It's ranking from tertiary down to secondary and primary. Okay, so in this case, the bromine will add to the carbon on the right here and get the tertiary radical here, which is more stable, and these tertiary radical, they draw it the other way. This is the same compound, okay, but they kind of switch left and right. They turn the molecule around, okay, and then this radical, tertiary radical, will add. Actually, it will attack the hydrogen here and get the products. So you can see here, the product, it has the bromine atom on the, I think this product is wrong, right? This one should be CH3. Can you change? This hydrogen should be CH3. And this hydrogen should be CH3 as well. They drew it wrong. Can you change this? This CH3 and this is CH3. Okay. I'm not sure if I can change it. No, I will not mess it up here. You just change this hydrogen to methyl group, this hydrogen to methyl group. And you see that the bromine is on the less substituted side. Okay. It's on the carbon that already have hydrogen on there, but the hydrogen add to the carbon that does not have a hydrogen to begin with. So it's called anti-Markovnikov product. Okay, so can you distinguish between Markovnikov and anti-Markovnikov product? You get this point? Well, there's a question, how do we know if it will be anti? If you look at if the structure of the product provided, you can tell right away by looking at the position of the bromine or hydrogen, whether it's on the right side or wrong side. according to the Markovnikov rule. Okay, do you understand? But if there is no product provided, they just provide starting material and reagent, you have to know what mechanism is the reaction undergo. Like when you have peroxide, you will get anti-Markovnikov product. But if you don't have peroxide, it's undergo electrophilic addition, it will give Markovnikov products. Do I answer your question? Okay. Okay, next is the addition of halide. Before it's hydrogen halide, now it's halide, okay? It's X2, which is usually either chlorine or bromine. I think iodine, we don't see much of the iodine reaction. It's usually either chlorine or bromine, okay? And the addition will give you the product. They intentionally draw the structure of the product to have the X atom adding from the opposite side, which is the anti-addition, which I will explain later how that happened. Okay, you remember that for hydrogenation, what type of addition do we get? Syn or anti? Hydrogenation. Syn, right? How about the hydrohalogenation? Do you get syn or anti? Hydrohalogenation. You get both, right? Because it goes stepwise. It goes through the carbocation, which the second atom can either add from above or below, which means it can add from the same side or opposite side equally. Remember? So you get racemic product. Understand? Okay. Now, this one gives you anti-products. So there's kind of detail of this type of reaction that it undergo through different type of mechanism to explain this. Okay. Here, for this compound, the addition of choline gives you this product. For this particular terminal alkene, either syn or anti, you will not be able to tell because you have two hydrogen here. Okay, you cannot tell whether it's syn or anti. Okay, but for this cyclic alkene, when you have syn and anti, you can tell the difference. If you add syn addition, if you have syn addition, what product would you get?
Trans นะครับ
If it's syn, you will get
อ๋อ
cis.
เป็นซิสใช่ไหมแต่ถ้าเป็น
Yeah.
แอนตี้เป็นทราน
But yeah, but this reaction undergo through trans reaction, trans addition. So you get the trans product. Okay, you should get trans product. They didn't draw it here, but you know you get trans. Okay, you will see it later. Okay, here they explain this by the using the mechanism of the reaction that there are several evidence for them to propose this type of mechanism. At the beginning, a lot of people do not believe this mechanism because it has some strange structure of intermediate, which is the called halonium ion, which have the halogen atom binding on both carbon to form cyclic compound, the three membrane cyclic compound here, with the cation on the halogen atoms. Okay, but because of the stereochemistry that they observe, that is anti, there's no other ways to explain this. And also they observe that in this reaction, you don't see any rearrangement occur, which means you don't get a free carbocation. Okay, the rearrangement usually observed when you have a free carbocation, but if you don't have free carbocation, you don't have a rearrangement. Okay, and the product is anti because the second halide have to add from the opposite side of the first halide, which already formed the ring on the carbon structure. Yeah. Okay. So the first step is the addition of the positive X. The second step is the addition of the negative X, okay, to form the anti-product. Here, so if you start with the cis-butene, what product will you get? You get bromine adding from the opposite side. Okay, you can have the first bromine on the up and the second bromine on the down, or you can have the first bromine on the down and the second bromine on the up. Okay, and these two compounds are enantiomers. So what you get is a racemic product of this compound, because it have a same chance for bromine, the first bromine, to go from above or below the alkene plane, and the second bromine will go on the opposite side. Okay. If you start from trans, you get also two structures here, but these two structures are the same, right? Because it has a, do you know what kind of symmetry does it have here from the drawing? Can you tell these two compounds these two structures are the same?
Yes.
You can tell, right? If you draw it, do you know about Fischer projection?
Yes.
Okay, if you draw Fischer projection, you have bromine on the same side, and it is a meso compound. Okay, but if you're looking at this structure, the zigzag structure, the symmetry element that you can see is inversion point here. Center of symmetry. You know center of symmetry here, that if you put a dot here as a center, you can draw the diagonal line from carbon to carbon, bromine to bromine, which is called center of symmetry or inversion point. That also signify the achiral compound. Okay. So these two structures actually is the same compound, okay? And it is a meso compound. So if you're starting from cis, you get racemic mixture. If you start from trans, you get meso compound. But what is the relationship between these two compounds?
Diastereomers.
Yeah, they are diastereomer. Okay, these are enantiomer and these are diastereomer. Okay, with the cyclic compounds, easier to see okay, the cyclic alkene. The addition, the anti-addition will give you the trans product here. You get the intermediate here as a colonium ion, which it could be the choline on the upside or the choline on the downside there, okay? And the second chloride have to attack from the opposite side of the first choline. So you get the trans isomer. And you get the both compound, which is enantiomer here, right? So you get racemic mixture of these trans product. Suppose if the reaction is syn addition, what type of compound would you get? It's just suppose, okay? It's not real. It's a supposition story. Yeah, you get the cis. And is this the cis compound chiral?
No, it's a meso compound.
Yeah, it's also the meso compound. So you can tell whether it's anti or syn addition by looking at the type of product you get, right? If you get two products which is a racemic mixture, then you can tell it is a anti-addition. But if you get the meso compound, which is a single compound, then it is a syn addition. So usually when they study about syn and anti-addition, it's easier to use the cyclic alkene. It's easier to see, okay? But it happens in both cyclic and acyclic compound. Just easier to see with the cyclic compound, okay? Okay, I think I should stop at this point for today, and we will talk about allohydrin formation in the next lecture, Wednesday. Okay, I think you have enough, have learned enough materials for the second homework. Do you have any question? We'll spend about maybe 20 minutes here for question and answer. Either from previous lecture or for this lecture.
So on Wednesday, we have a class because I thought it was a holiday.
Oh yeah, let me check. Oh yeah, next Wednesday will be October 13, right? So we don't have class. So it will be Friday, right? Next class will be on Friday. 15, yeah. Okay, we'll have class on Friday. Thank you. Okay, let's look at the chat. Any question in here? Will I have a key for homework? No, I will not have a key for homework. I think the homework, if you look at the slide and you come to lecture, it's quite easy. Can you explain? But you can ask, if you really don't understand, you can ask in the lecture. I usually save like 10 to 20 minutes at the end for question and answer. Can I explain the stability of carbon radical? How deep do you want me to explain? Well, how much did you learn about stability of the carbocation? Did you get any explanation, or you just memorize tertiary is more stable than secondary and primary? How much did Ajahn Valawut explain about this?
We just know that tertiary one is more stable because of the electron donating groups and of
Okay. So what you learn is that the LQ group, electron donating group, right? But you probably not quite sure how it's donate, right? I would probably can say the same for the radical, that because of the LQ group is electron donor and the radical is kind of electron deficient because you lose one electron, although it has no charge. Okay, it has no charge, but usually compound like to have pair electron, not unpair. So it like to have more electron to stabilize it. So any group that has a electron donating power will stabilize the radical as well as the carbocation. But it will go opposite way if it carbanion, but you haven't seen the carbanion so far. You learn about that probably for the organic chemistry too, when you study about ketone, carboxylic acid, derivatives, things like that, you start to see the carbanion there. Okay, so for now, the radical, the rationale for radical will go about the same as the carbocation. Okay, do I answer your question? But actually it has deeper concept about this, okay, to explain how the LQ group can stabilize it. How does it donate the electron? Actually, it's not really the electronegativity, it's something else. Okay. Can you explain about Markovnikov again? Well, the Markovnikov rule at the beginning, he suggests the rule according to his observation that the hydrogen, when you add hydrogen halide, the hydrogen will go to the carbon, which already have more hydrogen on there. But later on, after people know about the addition mechanism, electrophilic addition, which undergo through the carbocation, they explain based on the stability of carbocation that how the Markovnikov product form. But anything that will go opposite to the Markovnikov rule, they call anti-Markovnikov. Okay, let's go back here. Okay, let yeah. Okay, here. Let's look at this compound. Okay, if you do the addition of HBr according to the Markovnikov rule, what type of product would you get? Can you write on the slide? I think someone can write. Somebody already wrote on this slide before. What kind of product? Unfortunately, I don't have a pen to write it down here. I don't know if I can use this. Draw. Okay. Yeah, somebody do it. The double bond go into a single bond. Can you make that? Yes. That's a mechanical product. You should get that. But these, the product at the end, yeah, it's go the opposite way. As I said, can you change the hydrogen, this hydrogen to methyl group for me? Someone help. Yes, this should be methyl and this should be methyl. So can you see these two compounds are different position? This one, the bromine, go to the carbon that have more hydrogen, and the hydrogen go to the carbon that have no hydrogen. Okay, this one, the hydrogen go to carbon with hydrogen, and the bromine go to the carbon without the hydrogen here. So this one's Markovnikov product, and this is anti-Markovnikov product. Do you understand? Do I answer? Your question? Okay. Someone asked about the alkene test before the class next Friday. I cannot remember the due date. Can anyone tell me to confirm this?
It says 15th.
It said 15, right? So
Yes.
you have to do the test before that, right?
Okay. Can we do it at home? Like we don't have to do it on the 15th, right?
It will open for 24 hours. Do you understand? So before the due time, it will open 24 hours before the due time, but the test will be only like 10 minutes long. So you can do any time that you want. Okay, during that open time.
So it can open like on the 14th, right?
Yeah, it will open on the 14th.
Okay.
Yes. You can do daytime, nighttime. Yeah.
Is the test going to have like drawing?
It is have no drawing. It's multiple choice.
Oh.
The test will be a multiple choice. But the homework will be all the essay question. A lot of drawing. So hopefully it will help that you do a lot of drawing here. When you see the multiple choice, easier for you to do it. But because the time is quite short, so you have to be able to know it right away. After you read the question, you should be able to answer it. And you have 2 chances to do it. But if you decide to do the second chance, the score will be average, okay? And I have to say that sometimes it happens that you have bad internet connection and you lose the connection and you lose the point. But I cannot do anything. I'll go by the whatever is record on the system, because otherwise people will have a lot of excuse and it's very difficult for me to make a decision which should be allowed and which should not be allowed. So please understand that this point. Well, someone really want the key. Well, I don't think I will provide the key because I think it's pretty much in the lecture. If you're not really sure and you really need to know the answer, you can ask during this at the end of this lecture like this. As I say, because a lot of questions from the test will be very similar, or maybe even the same as a question in the homework. So I don't think if I provide the key and you just memorize it and go into the test and open that stuff would be very good for learning. But if you really want to know the answer and you don't really sure whether your answer is correct or not, you can ask here or you post your question in Q&A. You can do that. Any more questions? Okay, if not, then we will end the meeting for today and see you again on next Friday, right? Okay. See
Thank you.
Thank you.
You.
Thank you. Have a nice weekend.